On the 9th of January, 1857, the San Andreas Fault broke open across roughly 220 miles of Southern California. The ground moved sideways by up to 30 feet. Rivers changed course. It's still one of the largest earthquakes in the recorded history of the United States. And then it stopped. Not because it ran out of fault. There were hundreds of miles of loaded, ready San Andreas ahead of it. It stopped at one specific place, a gap in the mountains northeast of Los Angeles called Cajon Pass, and it did not cross. 45 years earlier, in December 1812, a rupture reached that same junction and went straight through it, taking a second fault system with it. Same place, same faults, two opposite outcomes. For a century and a half, nobody could say what made the difference. And it matters more than almost anything else about California, because whether the next rupture stops at that gap or crosses it decides whether the big one is a very large earthquake or something in a different category entirely. In June 2026, a team published a model that gives the first physical answer, and the answer is that right now, the gate looks open. Before the gate, the fault, and the San Andreas is not what most people picture. It's not a crack that will open and swallow California. It's a boundary. On one side, the Pacific Plate. On the other, the North American Plate. They're not pulling apart, and they're not crashing head-on. They're sliding past each other, sideways at roughly 2 inches a year, which is about the speed your fingernails grow. That is the whole mechanism. Two enormous slabs of the planet trying to grind by one another at fingernail speed, and failing, because friction locks them together at the surface, while the deep rock underneath keeps moving anyway. So the strain does not go away. It accumulates in the rock as elastic energy, exactly the way it accumulates in a stick you are slowly bending. Nothing visible happens for a long time, then the stick does not bend any further, and everything stored in it comes out at once. Los Angeles and San Francisco are on opposite sides of that boundary, and they are getting closer at that same fingernail speed. In about 20 million years, they will be neighbors. Nobody has to worry about that part. The part to worry about is that the southern section has not released in more than 160 years, and the strain has not stopped arriving for a single day of that time. Now, the first of the two earthquakes, and it is worth knowing how big it was before you hear where it ended. The Fort Tejon earthquake struck on a January morning in 1857. The rupture ran for around 220 miles through the southern San Andreas. In places, the two sides of the fault slid past each other by nearly 30 feet in a matter of seconds. Trees were snapped. The Kern River was thrown out of its bed. Ground shaking was felt across most of the state. California in 1857 had a population of around 400,000 people, almost none of them in the South. The rupture tore through country that was mostly empty, and the recorded death toll was very low. That is the only reason 1857 is remembered as a geological event rather than a catastrophe. Then the rupture reached Cajon Pass, and whatever it hit there, it did not get past it. The San Andreas segments south of the pass, the ones that run towards San Bernardino and on down into the Coachella Valley, did not move. That matters for a reason that has nothing to do with 1857. Those southern segments have now been sitting there, locked and loading ever since. Everything the 1857 rupture failed to release is still in the ground. 45 years earlier, something different happened at the same junction. In December 1812, a rupture came into the Cajon Pass region and did not stop. In the model published this year, it is treated as a tripartite junction rupture, which is the technical way of saying that all three fault sections meeting at that point moved together in one event. One earthquake on two fault systems at once. This is the crucial comparison, and it is the reason the whole question exists. The 1812 event was probably smaller in raw magnitude than 1857, but it did the thing that 1857 did not do. It crossed. So, the size of the earthquake is not what decides whether the gate opens. Something else is. Find out what that something is, and you are no longer guessing about the largest scenario for Southern California, you are calculating it. If you drive Interstate 15 out of San Bernardino toward Las Vegas, you go through Cajon Pass. It is a break in the range with a freeway running through it, a railway line, power transmission, fuel pipelines, and, on an ordinary day, a great deal of traffic. Most people crossing it have no idea what they are driving over. Underneath, two of the most active fault systems in North America come together. The San Andreas runs through from the northwest. The San Jacinto, which is a separate fault system with its own history and its own earthquakes, comes up from the southeast. At Cajon Pass, they meet. And here is a detail that surprised me when I read the paper. There is no continuous crack at the surface joining the two. You can't walk out there and follow a line from one fault onto the other. Whatever connects them is deeper down, and it is described in the literature as a mechanical interaction at depth rather than a single structure, which is exactly why it behaves like a gate rather than a corridor. A rupture arriving at that junction has to jump. Sometimes the jump works, sometimes it does not. Junctions like that have a name in earthquake science. They are conditional barriers. Not walls, not open doors. Barriers whose behavior depends on the state of the system at the moment the rupture arrives. To answer the question, you need to know how much strain is sitting on each of those three fault sections right now. And that is a genuinely hard problem because strain is invisible. There's nothing to photograph. The fault is doing nothing. So the team did something indirect. They built a physics-based model of the earthquake cycle in 3 dimensions and then ran it through time, which makes it 4. The model needs to know when the faults broke in the past because every past earthquake released strain and reset the clock on that section. So they fed it a 1,000-year history of ruptures for the region, reconstructed from geology, radiocarbon dating of disturbed sediment layers, tree ring records where ground movement damaged living trees, and written accounts for the last couple of centuries. Then they let the model run forward from 1,000 years ago to the present day, adding strain at the rate the plates actually move and removing it every time the record says a section broke. What comes at the far end is a number for each segment in 2025 of how much stress is loaded into it right now. It is worth being clear about what that is and is not. It's not a measurement. It is a model output, and it depends on the earthquake record being roughly right. But it is not guesswork either. It's the same class of physics used to design the things we build on top of these faults. The numbers that came out of that model are the reason this study made the news in June, and they're next. Subscribe and stay with me because the second half of this is about what happens on the other side of the gate. The stress is given in megapascals, which is a unit of pressure. The absolute figure is less useful than the comparison, so here is the comparison. For each fault section, the team worked at a range of stress at which that section has historically failed. Then they compared it with what is sitting there today. On the Mojave South segment of the San Andreas, the section immediately north of the gate, the historical failure range runs from about 1.2 to 2.7 megapascals. The modeled value for 2025 is 2.8. Above the top of the range, not near it, past it. On the North San Bernardino segment, the failure range is roughly 0.4 to 1.6, and the present-day value is 1.8, also above. The San Jacinto side is loaded too, high in its own historical range. And the summary the authors give is the sentence that traveled. Stress levels on multiple fault segments are now at or above the highest values seen in the past 1,000 years. This is where I want to be careful because this is the point where a video like this usually stops being honest. Being above the historical failure range does not mean the fault is about to break. Failure thresholds are not exact. The same segment has failed at different stress levels in the past, and there is no rule that says a fault must break the moment it passes some line. What it means is narrower and still serious. The system has more energy in it than at any time in the record we can reconstruct. So back to the question, what decides whether a rupture crosses? The intuitive answer is that a bigger earthquake pushes through and a smaller one does not. We already know that's wrong because 1857 was enormous and stopped, and 1812 was smaller and crossed. The answer in the model is stranger and more specific. It's not about how much stress there is on either fault. It is about how similar the two numbers are. When one fault system is heavily loaded and the other is not, a rupture arriving at the junction runs into a section that is nowhere near ready to move, and it dies there. When both sides are loaded to roughly the same degree, the rupture arrives at a neighborhood that is already close to failure, and it takes it with it. The gate is not opened by force, it is opened by agreement. Which brings us to now. The reason this study is uncomfortable is not simply that the stress is high. It is that it is high on all three of the sections that meet at that junction at the same time. The disparity is small. In the author's own interpretation, that convergence of high stress makes the pass more likely to transmit a rupture from one system to the other. The gate, as far as the model can tell, is currently open. Here's what it looks like if it happens. This is a scenario, not a forecast, and every second of it comes from how ruptures are known to behave. It starts as a patch of fault a few miles across, losing its grip. Not the whole thing at once. Earthquakes do not begin everywhere. They begin somewhere and then they spread. The rupture front travels along the fault at around 1.5 miles per second. That is faster than the shaking it produced, which is the detail that makes a large earthquake different from a small one. In a small quake, the ground shakes and stops. In a rupture running for 100 miles, the shaking arrives in one place while the fault is still tearing somewhere else, and it keeps arriving for as long as the tear continues. That is why the duration is the part that survivors describe, not the violence, the length. For a rupture of this size, the shaking in the worst places lasts somewhere between 1 and 2 minutes. Stand still for 90 seconds and imagine the floor not stopping. Within the first minute, the front reaches Cajon Pass. If it stops there, this is a very large Southern California earthquake, comparable to what happened in 1857, and the segments south of the junction stay locked with everything still stored in them. If it crosses, the earthquake stops being a San Andreas event and becomes a San Andreas and San Jacinto event. And this is where geography stops being abstract. The San Jacinto Fault does not run through empty country. It runs down through San Bernardino and Riverside, underneath some of the fastest growing urban areas in the United States, in the direction of the Coachella Valley. The 1857 rupture went through land that was almost empty. The same rupture today, taking the same path, passes underneath a metropolitan region of more than 20 million people. And if the gate opens, it does not take the same path. It takes a longer one through more of them. There is a second reason the location of that junction matters, and it has nothing to do with buildings. Southern California is supplied across the San Andreas, not near it, across it. Aqueducts carrying water from the Colorado River and from Northern California across the fault line. So do major electricity transmission corridors, fuel pipelines, gas lines, the interstate, and the rail freight route. All of it was built there because the terrain allows it, and the terrain allows it because a fault carved the gap. Cajon Pass exists as a route precisely because two faults spent millions of years grinding a hole through the mountains, and that hole is now full of the infrastructure that keeps a city of millions supplied. A rupture there does not just shake Los Angeles. It cuts several of the lines that Los Angeles is fed through at the same moment in the same few miles of ground. The buildings are the part that is on television. The lifelines are the part that determines how long the aftermath lasts. And Southern California has been quietly aware of this for decades. Reinforcing them is expensive and slow, and it competes for money with things that are on fire today rather than in an unknown year. Now the section that most coverage of this study left out, and it comes from the lead author. Lillian Burkhardt asked directly about what the model means, and this is not a prediction of when an earthquake will happen. What can be said is that the system is critically stressed, and that models like this one give a clearer picture of the range of scenarios to prepare for. That distinction is the entire difference between science and a headline, so it is worth spelling out. The model does not know when. It cannot know when. It tells you how much energy is in the system and which configurations of that energy have historically produced through going ruptures. Whether the next one happens in 11 months or in 80 years is outside what the method can say, and the authors do not claim otherwise. There is also a real limitation in the method itself. The whole thing rests on a 1,000-year earthquake record reconstructed from sediment in tree rings, and that record has gaps and uncertainties. Feed the model a slightly different history and the present-day numbers move. The authors are explicit about this. It is a range of scenarios, not a countdown. And there is a version of this story that gets told badly, which is worth naming because you will see it. Every few years, someone takes a study like this and turns it into an imminent warning. And when the year passes with nothing happening, the public quite reasonably concludes that the scientists were crying wolf. The damage from that is not abstract. It is the reason preparation money is hard to raise for something that has a 100% chance of eventually happening. So, what would actually close this question? Not prediction. Nobody serious is working on telling you the date, and the field largely abandoned that goal decades ago for good reasons. What is being worked on is narrower and more useful. Better paleoseismic records, meaning more trenches dug across the fault to find and date more past ruptures, which sharpens the input model depends on. Denser satellite and ground measurement of how the surface is deforming right now, which tests whether the modeled strain matches the real one. And better physics for what happens at junctions, which is exactly what this paper contributes. None of that tells you when. All of it tells you what to build for, and there is a version of this future where the gate opens and the outcome is measured in disruption rather than in deaths, because the things that crossed the fault were reinforced in time. That version is not decided by geology. It is decided by budgets decades in advance for an event with no date on it. Go back to 1857 for a second. A rupture 220 miles long came down the fault, reached that break in the range, and stopped. Nobody knows how close it came to going through. That is not a figure of speech. There is no way to know from the outside how near a rupture came to jumping a junction it failed to jump. What we do know is that everything it did not release is still there, and that the sections on both sides of that junction have been loading for more than a century and a half, and that the disparity between them, which is the thing that appears to decide whether the gate opens, is currently small. The fault is not waiting for anything. It has no schedule and no intention. It is two pieces of the planet sliding past each other at the speed your fingernails grow, and every day the stick bends a little further. The only real question is which side of the gate the next one ends on. And if you want the other half of this map, we made a whole video on the fault that sits in the middle of the country, 1,000 miles from any plate boundary, that has no business existing and produced 3 earthquakes strong enough to ring church bells in Boston. Start there.